Well, good afternoon everybody and welcome to DBAFundamentals Down Under for the March session. I'm your host for this month's session. My name is Warwick Rudd and today we've got Martin Catherall talking to us about In-Memory OLTP. What can it do for me? Now I'll hand over to Martin very shortly, but before I do, I've just got some housekeeping to run through.
Can we turn that off at all?
So first off, I'd just like to make a big call out to our sponsors, SentryOne. Without our sponsors, it makes it difficult to put on these sessions for you. So if you haven't already gone to the SentryOne website, make sure you go and visit them. They've got some fantastic materials for you to download and use. So if you haven't already gone there, make sure that you do and enjoy their products. Today's session, it is being recorded and will be available after the session. It won't be available straight away, but we will get it up on the archive site for you to be able to come back and review and use this session after the fact. Now we do have some call-outs for some regional SQL Saturday events coming up. First off, in just under a month's time, we've got SQL Saturday South Island on April 8th. We've got a couple of pre-cons that are up for grabs there. So a pre-con on a guide to HADR that can save your bacon, and a second pre-con on Power BI from rookie to rockstar. So if you're in the Christchurch area, make sure that you register for the SQL Saturday event, and if you want to come along to some great day of full day training on the Friday, register for either one of these two pre-cons. Then in May, we've got one here in Brisbane on May 27, and for that one, we've got a pre-con on Zero to Microsoft BI. So once again, these events are available for your registration, so make sure that you register, come along, and you'll learn from some fantastic local, interstate, and international speakers.
Sorry, to be on 2 minutes.
So the last thing, you're here because of PASS, you're already registered for PASS. There are many other virtual chapters that provide sessions just like this one, so make sure that you have a look at PASS to see what those other virtual chapters do provide, register for any other sessions that are available. So with that, I'll now hand over to Martin for him to start this session.
G'day, how's everyone doing today? Thank you very much for turning up. This is a pleasure for me to be here. Thanks for having me, Warwick. I've got a room full of people and it's going out live to you guys. So let's get into it. This session is In-Memory OLTP, what can it do for me? Pretty new technology. I just got a little sentence there on the screen about the crux of it is really that some people don't appreciate new technology and they seem to be able to not let go of the technology that they've been familiar with for quite a long time. So I'll just give you a bit of an introduction, and at the end of the session you can make your own mind up on what exactly it can do for you. So my name's Martin. The important thing on here is my contact details. Feel free to drop me a line. But one of the things I'd like to draw to your attention is that I volunteer as a past regional mentor, which means I know quite a bit about what's going on in the region, user groups, SQL Saturdays that Warwick's just talked about, and the like. So if you want to get involved with any of these things, drop me a line or drop Warwick a line, and we'll tell you all about the PASH virtual chapters. So the goals of this presentation are really just to give you a firm grasp of the basics of In-Memory OLTP. Try and move that out of the way. And to bring different perspective to this material. You've probably seen this session or sessions similar to this quite a few times. They all will tell you the same things, but I'll tell you in different ways. A lot of sessions like this show the difference in speed compared to traditional methods. I'm not going to do that. I'm just going to take the approach of telling you about objects and the like. And it's just to encourage you to think about the possibilities that lie ahead for this technology. What can it do for you, or what can't it do? It's really a rhetorical question, the title of this presentation. It's left to you to decide what it can do for you and what it can't do for you. So we're just going to go over three things really in this session. First of all, I'll introduce the basics. What's the syntax for in-memory OLTP and that sort of thing. Then we'll talk about data records, and we might talk about some internals. Is this the same as on-disk internals? And finally, we'll just talk about a few indexes. We've got one new index type, well actually two new index types, but one is substantially new. And we'll talk about those and how they work. So, where can you use this? If you've got SQL Server 2016 SP1, any version, even Express, you'll be able to in-memory OLTP. Up until 2016 RTM, well including 2016 RTM, it was just an enterprise-only feature. So it was in enterprise, developer and evaluation. It was brought out in SQL Server 2014, where obviously it was in only a few versions. But if you're playing with this technology, I'd advise you to get onto SQL Server 2016 SP1 and try and learn as much as you can. So if anyone's ever seen me present before in person, I like to make my sessions kind of informal and encourage questions from the audience. Obviously that's not possible in this format, but if you do have questions, just type them in and we'll get to them at the end. So I regard this technology as the database technology of the future. I think the way traditional SQL Server works with the buffer pool and all that is still going to be around for a long time, but we're kind of moving towards a new model. And one of the questions I get a lot is, well, SQL Server does everything in memory anyway. So is this just a marketing ploy by Microsoft to basically rebrand what SQL Server already does? And the answer is, well, yeah, SQL Server does more or less everything in memory anyway. But if you're familiar with how that cycle works, a page is read from on-disk into the buffer pool, locks and latches taken out, some processing done, and then wrote back to memory, back to disk. You probably find that this new model is slightly different, and it doesn't work with the traditional mechanisms that you're probably used to. One of the questions that comes up for me is how does this technology that I've just been over, traditional SQL Server, scale well? And obviously SQL Server scales very well. I've never personally hit any problems with scaling at all. But if we think about this, as we get more users, we get more requests to our SQL Server, we get more locks, more latches, more contention. As that happens, we probably then add more processes, more threads. That can probably contributes to more locking, more latching, and so the cycle goes on. And I guess that eventually, you know, do we get a great deal of benefit out of adding additional CPUs? Now, we'll see how this plays out. So is in-memory OLTP just simply about memory being faster than disks? And I don't think it is. As I've just said, the model has changed slightly, and it's as much about the model changing as it is about memory. If we look at traditionally, how things have gone traditionally with disk capacity versus memory capacity. You can see that disk capacity has always been much greater than memory capacity. For example, you might be looking at servers with a 1 terabyte drive and 128 gigs of memory. But the picture seems to be changing a little bit at the moment. Windows Server 2016, we can have up to 12 terabytes of RAM, which is a huge increase, and we can let our SQL servers take advantage of that. So the disparity between on-disk and memory allocations is not quite as pronounced as it once was. As we'll probably see through this presentation, disk is still crucially important, which is a little bit ironic, but we'll talk about that as we go on. Right, I thought I'd just start by introducing some acronyms and some language that are new to the SQL Server landscape and you may not have heard before. Probably everyone's heard of Hackathon. That was the code name for In-Memory OLTP before it got released. And the goal there was to try and make our queries over 100 times faster. Now, we haven't quite got to that limit yet, but it was certainly a very laudable goal. So In-Memory OLTP, I'd put the acronym down there, and Hackathon you probably hear interchangeably quite a lot. They effectively mean exactly the same thing. You'll hear people talking about on-disk rather than in-memory tables. You'll hear the acronym XTP. That stands for Extreme Transaction Processing. And if we go and look at like the DMVs or the X events, we'll see XTP in a lot of the names. Natively compiled, we now have natively compiled objects rather than our traditional TSQL objects, or as well as. Disk-based tables as well as on-disk tables. You'll hear people talk about traditional tables, which are effectively on-disk tables. Optimistic concurrency rather than pessimistic concurrency. We're optimistic that we won't get any lock-in and latching. We obviously have the optimistic on-disk with the row store, versioning and all that sort of thing. And we've got optimistic in memory. Often we hear people talk about legacy, meaning the traditional SQL Server model. I do find it surprising that people refer to this as legacy, but if you do hear that expression, you'll probably know what people are referring to. Operational analytics is something that Microsoft talk about a lot, and things like column store and in-memory are making big inroads into allowing people to do things like reporting and run analysis of operational data stores. HTAP, this is an acronym that I've only recently heard, and that stands for Hybrid Transactional Analytical Processing, which is very, very similar to operational analytics. MVCC, that's the name of basically the new model, multi-version concurrency control. Data is immutable, meaning it doesn't change. We'll talk a lot more about that as we go on. And checkpoint file pairs, or CFPs, are where the data is now stored if we choose to place it on disk. We've got a delta file there and also a data file. Also, one of the big things is ACID. People say, you know, does the database still perform to the traditional atomicity, consistency, integrity, and durability? And the answer is that even though it's a memory, yes, it definitely does. However, there you see I've got the D in brackets, and that's effectively to say that we've now got control over the durability aspect. No longer do we have to take durability as read. We can have no durability if we wish to. Okay, so first of all, we're going to dive into a demo, requirements for in-memory OLTP, and then we'll see how to quickly transform a table. So we'll just flick over to Management Studio. Now, one of the things I learned was that I don't have enough ports for my mouse, so I'm using a keypad. So hopefully that won't slow me down too much. Now I'll just open all of of our demos here. And I'll create a simple, sorry, I think I opened the wrong demo. Right, we're on. So first of all, I'll just create a traditional database. And we'll see that the only thing we need to do to enable a database for in-memory support is to create a file group. Now it's a little bit different than we would traditionally keep a file group. All we need is a name for the file group and basically a file name. The file name is not really a file, it's simply a container, a folder on memory, folder on disk where objects can be stored. In this file group we can have as many basically as many containers as we want, and we might wish to have that just for scaling ability. However, as we'll see from the next example, if we wish to have more than one in-memory file group, well, that's not possible at all. We can only have one in-memory file group per database. But as soon as we've got the in-memory file group, the database is built and ready for in-memory OLTP. Right. So there we see how we can enable in-memory OLTP. That was a create database statement. We can do exactly the same thing with an alter database statement. Obviously, we add the file group and then we add a file to that file group. Okay. So what I'm going to do now is simply create two on-disk tables, just traditional on-disk tables, nothing particularly fancy about them. You can see the syntax I used there. And we're just going to flick back to Management Studio and show how to transform those into in-memory tables. We'll go to our database tables. Now, as you've probably worked out, the first one is going to fail. And it's going to fail for a pretty good reason, so I can demonstrate a certain feature here. As soon as we open the wizard, we're met with a load of scenarios that run over our table to say if it's got any features which are not supported. This particular table has got two features. It's got an unsupported data type, which is XML, and also it's got an identity column, which is allowed. However, the increment of the identity column is not allowed. We're only allowed to go up in increments of 1. Now, the reason I chose to show this as a failure is because you'll notice over towards the right-hand side of the screen you've got a Show Me hyperlink. Now, just clicking on there will take you to a web page which will show you more about why that particular feature has failed. So that's some really good data you can get off this wizard, and it's a really good way of learning. But I'll just cancel that because obviously, as you can see, now it's failed. We can't go any further. So now we'll get into showing one that will actually work. The first screen, we get our diagnostics run over as we did the first time, and they failed. The second screen will just show us some information about things we might have in that table. Doesn't really stop us from implementing any in-memory OLTP data. It just basically gives us heads up that if you've got any of these things in your table, you probably want to go and check them. So again, we've got the links where you can go and check out more information. Now things start getting interesting on the next screen. We can see up the top here, we can provide some information so our file group will be formatted correctly. The next part of the screen is basically just to say if you want this table transferred, what you want me to call the old table, and do you want me to transfer your data. It's not really that important, you can do that manually. But the next checkbox is really important. So we've got, by default, this table would be migrated to a memory optimized table with both schema and data durability. They're new words, we've not heard them before. So we can check this box to migrate the table to an in-memory table with no durability whatsoever. And all that basically means is that the data will be held in memory. That's the only place it will ever be. As memory is transient, if the database is kind of offline and then online, or the server is switched off, or we're backed up and restored, all the data in that schema-only table will be completely lost. Obviously, that rings a lot of alarm bells for some DBAs and developers, and quite rightly so. However, if we choose not to accept that, then our data will be persisted. The data will still be held in memory, but as we change the data in the table, that will be wrote out to disk to what we call checkpoint file pairs. Totally different place than our traditional MDF and NDF files, and we'll have a look at that very shortly. The next step of the wizard, we get to choose index types. Now the index type down here, the non-clustered index, is what we call a range index. Very, very similar to our traditional B3 index is. Has a few slight differences, but essentially it's very, very similar. The index that is quite different and brand new here is the non-clustered hash index. We're going to look at this in quite some detail later in the presentation, but for now, all that's important to know is we must specify the amount of what's called hash buckets. So I'll choose 20 there. I'll pick that as the ID, and and we'll move on. At the end of the wizard, we can choose to either migrate this, or we can choose to simply script it. I'll script this off, and then we can go have a look at what has been produced. We can see down here that the syntax is mainly what we're used to for creating tables and that. However, the interesting bit happens here. We've got with memory optimized. We've got a new feature called memory optimized equals on, which signifies this is in fact an in-memory table. And our durability is also specified here. We chose schema and data, so we're going to persist our data to disk. If we only wanted to have it in memory, we would simply choose memory only. We can also see that the constraint has been placed in line in the table, and that's some really good syntax that I like that came along in 2014. So that's a really good way of learning how to interrogate in-memory tables and see what's and see how to go about doing it. So I'd advise you to dive into that wizard, get to know in-memory tables a little better, and see exactly what you can do and exactly what you can't do. So let's just flick back to the presentation. And one of the things I like to do in some of my presentations is just to give a little quick quiz, just to consolidate what we've just talked about. So obviously you can't answer these, but we'll just go over them very quickly and just think in your head, is that possible or is it not possible? I'll just create my in-memory database there. First question I throw at people is, would this create an in-memory table? Well, the answer here, and I hope you can all see it, is no, this would not create an in-memory table. Although we've got the syntax down the bottom to create a table, we can see that there's no index in this table whatsoever. And one of the criteria for an in-memory table is that we must have at least one index. We'll move on to the next one and we'll see, would this create an in-memory table? We do obviously have an index here. We've got our primary key. However, this will not create an in-memory table at all, and the reason is that clustered indexes are not allowed in in-memory tables. And obviously the default for a primary key is a clustered index. So that, as we can see, will definitely fail. Our fourth option, here this will actually pass. We created our primary key again, but this time we've specified we want a non-clustered primary key. So this will create a range index for us. This looks a bit complicated, and what we're doing here is trying to create a table with quite a lot of indexes. Now we can create any number of indexes as long as it's below 8. Here we've actually got 9 indexes attempted to be created, and this is basically not allowed in in-memory tables. We can have a maximum of 8 indexes on our table. So that will totally fail. Okay. So hope you got those all right, and maybe that helped consolidate some points. Okay, so just to clarify, in-memory tables, the database needs an in-memory file group. We can only have one, and our data can either be persisted on disk or just rest in memory. If it just rests in memory, it can be potentially lost if the server is basically taken offline or backed up and restored, and that might be fine. One of the scenarios that is often talked about here is like session state data or transient data that we might have in our database. 2 notes I put down the bottom there. I put no index maintenance. Basically, fragmentation in in-memory tables is a thing of the past. Stats need to be updated manually. They're created at table creation time, but obviously at table creation time we have no data in our database. As data is added continually, what happens with a traditional table is that the stats are updated in line with a certain algorithm. That doesn't happen in in-memory tables. It's left totally up to you to update the statistics when you want to update them. Now we've got data in our database, what we'd want to see is how do we access that data. TSQL is fully supported in almost any situation, and we'll have a look at one situation where it's not probably the optimum thing to use very soon. So is there an alternative to traditional TSQL? And the answer is there certainly is, and it is TSQL again, but another form of TSQL, what we call natively compiled objects. So natively compiled objects just basically produce DLLs. The DLLs are recreated at startup and placed into the memory of SQL Server. Now natively compiled objects, although they're built with traditional TSQL, they can only actually access in-memory tables. And there's a similar wizard for converting your stored procedures to natively compiled objects, but I actually find that it's a lot less useful than the table optimization wizard. And if you do choose to convert your stored procedures, you probably would want to do this manually to check the consistency of your results. So let's dive in and have a look at a natively compiled stored procedure. Okay, so I'm using here the new syntax of SQL Server 2016, create or alter the procedure. That's obviously not specific to natively compiled stored procedures, But stored procedures obviously are the main objects that T-SQL is used for. And we'll see here we've got to have the declaration with native compilation. Natively compiled objects must always be schema bound. We don't want tables or other objects that this refers to suddenly disappearing. And there's an optimization put in where we must say the execution context that we need. That's all there is to the start of declaring a natively compiled stored procedure. The only other requirement is that it must go in a begin and end block, and we must tell it that this is an atomic transaction, and we must define the isolation level. That's the only requirements to creating an in-memory or a natively compiled object. Inside the natively compiled object, we can have any T-SQL that is allowed. Now, T-SQL is basically being ported over to our natively compiled model. So every single piece of T-SQL is not yet implemented, and so every single piece of T-SQL will not actually work against in-memory tables. Some of the better known aspects that wouldn't work would be case statements and subqueries. So if you see any of those, you might want to stick with traditional T-SQL at the moment. Obviously the limitations will be taken away over time, but at the moment that is a limitation and something that's a little bit of a blocker, but hopefully within a version or two that will be gone. Triggers are very interesting, I think, and I spoke earlier about times where you absolutely have to use natively compiled objects, and triggers are one of those places, because if you've got a natively compiled table, the only thing you can put on it in terms of triggers is a natively compiled trigger. Now, one of the things you can only do in natively compiled objects is access other in-memory tables. So from a natively compiled trigger, you can't actually access a traditional T-SQL table. And that could be a limitation for some people. So let's have a quick look at natively compiled triggers. I'll just basically dig a trigger out here to show you how they work. All these scripts will be available afterwards, and you can probably work through all these examples in your own time. What I'm going to show here is just trying to create a standard trigger on an in-memory table, and we'll see that it absolutely doesn't work at all. If we want to create an in-memory trigger, what we have to do is basically just add in similar concepts that we did with the in-memory stored procedure, with the native compilation and the atomic block again as well. So let's move on to talking about data records. And surprisingly, data in an in-memory table is immutable. When we get immutable data, the data absolutely cannot change at all. So what does this mean? This basically means we must make a new copy of the data as it changes or is updated or deleted. So we'll have a look how to do that. As a new record comes into the database, a new record is created to replace the existing one. That existing one is no longer needed and is marked for what we call garbage collection. And for those that are familiar with any .NET language, you'll probably heard of garbage collection previously. And this is one of the reasons why Microsoft say if you've got an in-memory table, you should probably leave at least twice as much memory as that table needs, because when data is modified, that duplicates the records momentarily until they're garbage collected. So the amount of memory needed is actually greater than the size of the table itself. Schema-only records, they never go to disk, so they're not persisted. And with schema and data records, that data is streamed to the containers that we've seen previously and sits on disk in a checkpoint file pair. So this is what our data records look like. They're basically split into two main sections. There's a row header and a payload area. The payload area is basically the data that we've chose to put in, whatever data that is. So we're not really going to dwell on that area of the record at all. What we're going to look at is the row header. And there we can see that the row header is made up of a few different objects that all have relevance to how the record is dealt with. So let's have a look at this. We can see that first of all we've got a begin timestamp and we've also got an end timestamp. As a new record goes into the database, the begin timestamp is written, and that is basically the time of the transaction that committed the record. The end timestamp, well, that will only be written when the record is deleted or it's modified. The statement ID is basically an internal helper that deals with something called Halloween protection. If you've never heard of that, that's basically just a mechanism that stops SQL Server or database in general from reading the same record multiple times. We then have an integer value that's basically just a count of the indexes that are used on this in-memory table. And lastly, we have pointers to each of the indexes that exist on this table. The important thing in this diagram is really the begin timestamp and the end timestamp. So when a row is inserted the first time, we'll see our current timestamp is written over to the left, and our end timestamp is marked with a special symbol. I'll call this infinity, and that basically signifies to SQL Server that this is the current record. When that record is modified or changed, something happens. We look at the case where it's deleted first. When a delete statement is run, basically the end timestamp is updated to the timestamp of the transaction that deleted the record. The presence of that timestamp signals to SQL Server that this record is no longer needed and is available to be garbage collected. So let's have a look what happens with an update statement. We've seen what happens with an insert statement and a delete statement, but what happens when data is updated? Well, we'll start with our record that's just been created. We've got obviously the begin timestamp and the infinity mark, which signifies that this is the current record. As that's changed, a new record comes in. The transaction ID, transaction timestamp of that new record basically deletes the old record. So the old record has its end timestamp written. This signifies to SQL Server that that record is no longer written at all, and the top record gets an infinity mark for the end timestamp, and that signals to SQL Server that this is in fact the latest record and the one that we need to use. If other people are using the previous record for other transactions, that's fine. It'll just hang around until basically no one else is using that record, and then it will be garbage collected. So the top one now becomes the current record, and the bottom one is available for garbage collection. This pattern is termed the multi-version concurrency control. and it's, as you can probably see, it's quite different from the traditional buffer pool model. Data is immutable, and think inserts and deletes. We don't think updates, because an update is basically an insert and a delete. And remember, the rule of thumb is twice as much memory as the table needs. So let's take the example where the table is 1 GB big. We're best to give our database 2 GB of memory to allow for transactions, updating records, and multiple records existing at one time that are going to be garbage collected. But like it says on here, your mileage may vary, so please test. Let's move on to indexes, because I think indexes are quite an important feature. And as we've noted, we can only have non-clustered indexes on the table. Well, actually, that's not quite true. We can actually build a column store over the top of an in-memory table. That's probably outside the scope of what I'm talking about in a minute, so I'll just concentrate on the fact that we're going to deal with our two new index types, which are hash indexes and range indexes. Range indexes are very, very similar to our traditional B-tree indexes. However, indexes in memory are simply single linked lists. There's no doubly linked lists, so we always specify the direction in which we want the pointers to go, either ascending or descending. And you might have seen that in the wizard that we stepped through earlier. Quick note about range indexes. Like I said, they're very similar to B-tree indexes. They're actually termed BW tree indexes. Linkages are one way, and as with all memory objects, they are lock and latch free. And as the name suggests, they're great for range scans, which is different than the intent for our hash indexes. With hash indexes, they're absolutely great for point lookups if you're looking up one value based on an equality clause. Now, we need to define what is called a bucket count, and basically we should have one bucket per unique value. So if we know we're going to have, say, 100 unique values in the database, we should have at least 100 unique buckets. However, the recommendation is, because we can possibly have collisions when hashing objects, to have twice as many buckets as we have unique values. So in that particular example, we may want to have 200 unique buckets. We'll get into talking about this further on the next slide. For composite indexes, the hash is calculated on the entire index, on the entire columns. So say, for example, we have an index on first name and last name. If we're going to look up on those values, we actually need to look up on first name and last name. Simply looking up first name is going to be of absolutely no use to us whatsoever. So we have to look up based on the columns. Like I say, these are great for point lookups, equality searches. And I think they're probably a pretty good candidate for using with unique indexes and primary keys. Although you can obviously not have unique indexes or primary keys, just traditional indexes with these types. So let's have a look at how this would work. We've got a table here just full of 4 names. Obviously this is a bit of a contrived example, but it bears a good analogy to how things would work in real life. So SQL Server looks at this table and then it says, right, I'm going to build a hash list, or basically a bucket list of unique values. So for each value in this table, so for each unique value, it will build a hash. So it hashes the name Martin, hashes the name Albert, and hashes the name Paul. Now, I've not built a hash for Robert because I want to demonstrate a collision, how that would work. So for each unique, when I say unique value, I'm talking about the unique hash value, not the fact that Martin, Albert, Paul and Robert are all unique in themselves, but when those values are hashed, is the hash actually unique? And in our case, we've actually only got 3 unique hashes. So we enter the value Martin, and that goes in the first hash bucket. I've signified it here just with a little link or pointer. We put in Albert, and that will go in the Albert bucket. We'll signify Paul, and that basically goes into the Paul bucket. Now if we were to put any of those values in again, obviously they would hash to exactly the same value and end up in exactly the same bucket. However, in this example, I'm going to place the value Robert into the table. Now, unfortunately, Robert hashes to exactly the same value as Martin. So it goes into exactly the same bucket. So when SQL Server comes to look this up, obviously I'll hash the value, go directly to the hash bucket, and then it'll have to read through a chain to find what values are Martin. Not a massive overhead, but something that we try to avoid. We can avoid this by making a large value of hash buckets. So if we know we're going to have 1 million values in our table, try and make 2 million hash buckets as a rule of thumb. So let's just have a look at some syntax about how this would work. We'll create our database. And we'll create our table with our hash index. Now we see here that we can just define these in line. And all we need to say is non-clustered hash with bucket count equals whatever the bucket count is. One of the things that this example shows that probably shouldn't happen in real life is that the primary key bucket count is 3 and the non-clustered hash index count is 100. Basically, they probably should be exactly the same because there's going to be no real difference in the amount of records they hold. One interesting thing about the amount of hash buckets is they're always allocated in powers of 2. So for example, the powers of 2 would go 2, 4, 8, 16, 32. So if we specified, say, 20 hash buckets, the next value of 2 above that is actually 32. So we'd actually get 32 hash buckets and not 20. Just a little piece of information that you might want to take into consideration if you are planning to create these hash buckets. And like I say, a good use for these is primary keys, because obviously primary keys are unique, but you've got to take into consideration, are you going to use your primary key for a dedicated equality search? Because if you're going to range scan on this value, you're probably best just making a range index. These hash values are very good for point lookups, but are not really meant for range scans or ranges of searches. So we've got range scans for one thing, hash indexes for another. Okay, So we're getting to the end of the session here. So let's summarize. In-Memory OLTP, I've found through my own examples, is really good for high concurrency workloads. I personally never got to the point where I've seen SQL Server fall over or anything because concurrency is so immense. But as we get more data and people doing more things with data and doing different reports, different analysis, and so forth, we have got different workloads running against our databases and greater concurrency. So in-memory OLTP may well come to the rescue here. We don't have to persist data. The choice is now ours. So the data endurability is now a choice rather than something we have to have. If we don't want to persist data, we just do schema only, meaning the data will be lost if our server reboots for any reason. An interesting point that I've not mentioned in this this presentation so far is that pure in-memory usage does not use tempdb at all. So if you're going against a pure in-memory table, and I'm not talking joining to an on-disk table or any on-disk tables being involved in this at all, if you're just pointing and querying totally a in-memory table, then tempdb usage is not done whatsoever. You'll see most of your speed with natively compiled objects going against in-memory tables. Obviously, you'll get the speed of mixing the two things, natively compiled code against in-memory tables. When we use TSQL, traditional TSQL, not natively compiled, this can be a little bit slower. And that's because it goes through a process known as interop, where it's effectively interpreted into language that can be used against our natively compiled tables. If you use DBC CheckDB, or in fact any of the DBCC family, against a database with in-memory objects in it, you may be forgiven for thinking that CheckDB actually checked those objects, when in fact it actually skipped over them and never checked them at all. So just be aware of that if you are using in-memory tables. An interesting point is that you can't truncate an in-memory table at all. Running a truncate table statement against an in-memory table will result in an error. But deletes are extremely fast, as I'm sure you probably can appreciate with in-memory. It's just a block of memory that needs to disappear. And we can't mix on-disk constructs and in-memory constructs. And I guess one of the more obvious examples there is an in-memory table. You might want to reference a key in an on-disk table. Maybe have a relationship between an on-disk table and an in-memory table. That is not possible at the moment. So please be aware of that. In all the presentations I've done on this, and this is my first remote session on this, but probably I've done 3 or 4 sessions in the past, I've never come across anyone who's making a pure in-memory workload. So I put in some references in here that you can feel free to go away and browse at your leisure. You'll find much more information than I've given here, and there are 2 books that I'd highly recommend. The one on the right is totally free. It's 2014 book at the moment, but it's no doubt being updated for 2016. That's a free download from the Redgate site. And the second one you'll have to purchase, but it's a top quality book, Expert SQL Server In-Memory OLTP. Both references that I've used in the past. One other reference which is pretty good, if you have a Pluralsight subscription, there's a guy called Russ Thomas on there who does an excellent in-memory OLTP course, and we'll drill down into much more of the details that I've given in this 1-hour presentation. So I'd like to thank Warwick for having me here, and say to all you people, if you would like to visit the website of SQL Down Under, please do so. We've got some fantastic tools on there that can help you guys in your analysis and development of SQL Server objects. So thanks for your time, and thanks for having me, Warwick.
Thanks, Martin. So to round out, we do have some questions for you. So let's just go through those. So how will OLTP take care of abrupt server shutdowns? Does this mean that it is moving away from the two-phase commit, where the SQL Server is supposed to write to the file first?
Okay. Now, in short, no. The end result is exactly the same as happens at the moment. I mean, what happens with traditional tables is you've got your basically write-ahead logging, where the log is wrote to momentarily before the data files. The same sort of thing happens with in-memory OLTP. It's just addressed in a slightly different way. Probably not got too much time to go into the details right now, but yeah, basically the end result is the same. So that's one part of the question. The second part of the question is, I think, what happens with an abrupt service shutdown? Well, if you've got schema-only data, where the data is only held in memory, then you will effectively lose every single piece of data. Won't be able to be recovered whatsoever. However, if you've opted to have schema and data, when you've obviously changed your data, as well as being changed in memory, it's also been written to the log and written to checkpoint file pairs, which are held in a different location than traditional MDF and NDF files, but essentially the data is still safe on disk. So the combination of those checkpoint file pairs and your log is enough to bring the data back to the point where it was shut down. Hopefully that answers the question.
Okay. So what types of tables are candidates for in-memory OLTP? I see a limitation of 8 indexes. Isn't that too restrictive for core tables?
I guess yes and no. Depends on your scenario. Like I said in the summary, I guess high concurrency tables. Obviously, if you've got an application similar to SharePoint or something, where you've got many hundreds of columns in your database, it probably is somewhat restrictive to only have 8 indexes. So I guess it will depend, like everything in SQL Server, on your use case and your workload. Will that restriction disappear over time? Maybe. I guess there's a big gap between the amount of indexes that are available on disk tables and the amount of indexes that are available in memory tables. Hopefully that gap will close. I'm guessing it will. I mean, if we look at a feature, say, like column store that came along 4 years ago, it's took 4 years to get to, well, I feel, a vastly superior product. In-memory OLTP, well, that's been around just over 2 years, just over 2 versions. Has it got a way to go? Yes, certainly has. But is it moving in the right direction? I think so.
Okay. Will the amount of data in an in-memory table noticeably impact the instance at startup time?
Yeah, that is a great question. Probably something I should have addressed in the presentation. And the answer to that is yes, it potentially can. it potentially could. Obviously, when the server is switched off, if you're persisting your data, that data is stored in basically in the checkpoint file pairs on disk. When the server's started up, that data has to be read from disk into the in-memory table. Now, if you've got, I don't know, maybe a table that's not that big, the overhead of that is probably not great at all and probably not noticeable. However, if you probably got a terabyte or two's worth of data in a table, then I'm thinking that the overhead of that is probably going to be noticeable, and it's something that DBAs are going to want to take into consideration when having to reboot their servers for things like patching. So the answer to that question is definitely yes.
Okay. Are we able to use in-memory OLTP across two databases?
Across two databases? Well, I wish that was the case. The short answer to that is no. You can't do, you basically can't work in that scenario at all. I got caught out doing one of my demos one time, not particularly for here, for another session. I tried to load data from AdventureWorks into my in-memory database, which was a totally separate database, and immediately there was an error saying that cross-database queries are not supported. So the answer to that is no. Again, will that limitation disappear over time? Possibly, yeah, but at the moment that's not possible.
Okay. What are the disadvantages of a hash index?
Well, I see one of the disadvantages of being, well, one of the advantages, let's say first, of just doing point lookups very, very quickly based on equality searches. Okay, so that's all you want to do for your index, then that's great. A hash index is obviously for you. If, however, on that column, you might want to look up, say, first names between Martin and Zebedee. A hash index is probably not the right thing for you there, because it would basically be looking up every single value between those two values. So yeah, a range index would be better there. Also, when values are hashed, they, you know, like in our example of names, we can look at a list of names and put them in alphabetical order, but the hash bears no relation to the order that we would put them in as human beings. It's basically a machine-dependent thing. So, I don't know, very quickly there, what I see the two main differences, and that you can define that as being a limitation or an advantage. You can build a range index on the same column as a hash index, absolutely no problem there. Like with everything, your mileage may vary, and testing will bring this to light.
Okay. Are you able to roll back or revert a table from an in-memory OLTP table back to a disk-based table?
Okay, yeah, that's an interesting question. Well, if you, I don't know, if you probably noticed in the demo, although I probably referred to it as basically changing a table from a disk-based table to an in-memory table, it wasn't really a change. Basically, there was a brand new table created. The existing table would have been renamed, and any data that was there would have been copied from the existing table into the new table. Now, obviously, you can go through exactly the same process the other way around. You'll probably have to do that manually. There's no wizard for doing that, but there's no reason why you can't. So, but the question does bring up a very good point that might not have been obvious from that presentation, in that we don't actually change the table from an in-memory table, from an on-disk table to an in-memory table. There is actually a process of creating a new table, loading data into it. Yeah, so it's basically the same thing, just the other way around.
Okay. So can you explain CFP in more detail, please?
Yes, I can explain CFP in a bit more detail, and I will just mainly flick over to CFPs stands for checkpoint file pairs, and they exist on the file system in the folder. Let me just find a place where I know there are some here. They're basically the place where your data is stored if you choose to do schema and data. And here we're looking at a container that I created during the presentation. Inside we'll see basically this relies or uses some of the file stream technology quite heavily, not as heavily as it did in 2014, but that still underlies the mechanism. So we'll see two folders here. One folder they both contain files to do with the data. One folder will contain any changes we've made to data, and the other folder will contain data. Now obviously there's nothing in there. That's because when I created a database I never created any data. In fact, I think in the whole of the presentation I didn't create any data at all, but let's have a look at a few more. I might have created a few in here, and we'll see that basically the checkpoint file pairs are randomly named with GUIDs. They've got a certain extension. If we open them, we'll just see basically there's gibberish inside there, but they are effectively where your data is stored on disk. So your data is no longer stored in traditional MDF and NDF files in the location where you put them, where you create table statements. It's stored in a container that you provisioned when you created your file group, and depending on the amount of data you've got in there will depend on the amount of checkpoint file pairs you have within this container. So like I say, if you do want to know more about this, go check out Caelan Delaney wrote a great white paper. It was originally wrote for 2014, and I think it's been updated to 2016, and that will deal with checkpoint file pairs in a lot more detail than my 2-minute explanation there.
Okay. How much memory size would be an ideal size to have on a production server?
Okay. In all the presentations I've done on this, I've never met anyone who was running a 100% in-memory application, and very few people who are using this in production in the first place. But as I don't know, my gut feeling, and I obviously could be totally wrong here, my gut feeling would be maybe terabyte or 2 would be a big table. With SQL Server 2016, with Windows Server 2016, you can have up to 12 terabytes of memory. Now, I did mention about twice the limit for the table, so that takes us down straight away to 6 terabytes. Obviously, you're going to want to leave things for space for the operating system. That probably knocks I don't know, maybe let's say knocks a terabyte off that, and maybe you'd want to just for safety go a little bit below that. So for one table, I don't know, I think I've read somewhere about testing that was done with a 5 terabyte table. Again, that was only a blog post on the internet, but it seemed to say that that was possible and useful. How how good that would be in reality, well, I don't know. I've not worked on any systems that big. The tables that I've worked on have been in the range of gigabytes rather than terabytes. That seems fine. But like I say, this is a new-ish technology. It's obviously pretty robust, but if you want to get bigger than that, or even if you don't, testing is probably the thing to do.
All right. Thank you, Martin. Thank you, everybody, for coming along and being part of this session. Just to reiterate to everybody, this session has been recorded and will be made available on the DBAFundamentals archive site. That will probably be in a week's time. Also, the slide deck and the scripts. Martin, are you able to provide those so that we can put those up as well?
Yes, I sure can, Warwick. I'll get them to you in the next hour or so.
Excellent. So everything from today's session will be made available to you on the DBAFundamentals archive page for this month's session. So with that, I'd like to thank you all and look forward to seeing you all again next month, same time, for our April session. Thanks, everybody.
Thank you.